and welcome to the Quantum Mogul podcast. I'm the co-founder of Quantum Mogul, Jasmine Surya-Rachi with
and Donald Kelleher.
And it is a profound delight and a real honor to welcome Dr. Bob Sutor to the show. Welcome to the show, Bob.
Thank you. Glad to be here with you.
And just one of our biggest challenges is because Dr. Sutor is so prolific, because he's done so much in his career, is to try and condense his biography. So we are going to make sure in the show notes that you get a link to you can connect with Dr. Sutor, as well as his full biography and also his full resume. What he has accomplished, what he has achieved is nothing short of just simply magnificent when it comes to what we talk about here at Quantum Mogul, a legacy founding the future now. So just sharing a little bit about Dr. Sutor. He's been a technical leader and executive in the IT industry for over 40 years. He has over 20 years, is that correct, Dr. Sutor, with IBM? And now you're with Inflection?
Actually, 39 years.
Oh my goodness. I'm glad you corrected us there. 39 years. So we're going to hear a lot about that, I'm sure. And is now with Inflection. His goal is to evolve quantum to help solve some of the critical computational problems facing society today. Dr. Sutor works with industry analysts and investors to accelerate understanding and adoption of quantum technologies. He's now the vice president and chief quantum advocate. I love that, quantum advocate at Inflection, Cold Quanta. And he's going to tell us all about what they're up to. It's a hardware and software company working on quantum computing and sensing. He's also an adjunct professor in the Department of Computer Science and Engineering at the University at Buffalo, New York. He has spent, as he said, 39 years with IBM Research. During his time, he worked or led efforts in symbolic mathematical computation, optimization, AI, blockchain, and quantum computing. He's a theoretical mathematician by training, which I have so much respect for, because that is not my area of genius. And he has a PhD from Princeton University with an undergraduate degree from Harvard College. I love that he's an author, and we're all about education here at Quantum Mogul. And here is where you can learn more from Dr. Sutor. He has written two books. One, a book on quantum computing called Dancing with Qubits, that was published in 2019. And he's also the author of the 2021 book, Dancing with Python, which is an introduction to Python coding for classical and quantum computing. And that's an interest of mine, so I'm looking to pick that up myself. So we're going to put the link in to where you can learn from Dr. Sutor's genius in the show notes below. Welcome to the show. And our first question is, we have to ask everyone, what drew you to quantum? Why are you so passionate about it personally?
Well, for most of my career, and as you described it, if you hang around long enough, you do a lot of stuff. so your resume tends to have a lot of items. I was always attracted, certainly things that had a mathematical basis, but also that had a leading edge technology basis. I was always interested in what was coming next, what was going to shape the future, as opposed to something strictly operational of things we're doing now. And that goes to my being a theoretical mathematician, at least by training, of at least at that point, not worrying about the immediate applications, but what it would be used for eventually. IBM, where I was for many years, actually had been thinking about quantum for many years. In fact, the term quantum information science was coined in February 1970. By an IBM research scientist. So 53 years ago, right? So that's a little bit of a legacy. So whatever I've done, if you will, you use the word pioneer, I'm at most a later pioneer than many of these people. But really, starting about 7 or 8 years ago, I started to become aware of some of the work IBM was doing in quantum. Now, I was at IBM research headquarters in Yorktown Heights, New York. It's a very large building. It's a beautiful mid-classic, mid-century modern building. And I was way down at one end, aisle 32. I led the math department. And well, they put the physicists and all the people at the labs and things that could explode, right, way down the other end. So there wasn't always a lot of mixing, but by an organizational change, we all reported to each other. And so I started to learn more about what they were doing with the physics of quantum computing and building quantum computers. Now, I'm not a physicist, as most people who spent any time with me realize very quickly. My perspective is very definitely mathematics and software and computer science. But it seemed really interesting. And in fact, within the math department, I started a group that was focusing on quantum algorithms and quantum software. For me, intellectually, I didn't know anything about it. Wow, this is fascinating. I'm attracted to it. And I knew there was a lot of mathematics to it. And I also knew, as has always been the case, for computing to be successful, you have to have good software. It's one thing to create all the hardware, but what's the software foundation for doing all that? So by organization, by interest, I was attracted to that. And then as the program grew, I was one of the very few people who had both research leadership background as well as business leadership. I was on the business side of IBM for 13 years.
Wow.
So if you're thinking of starting a big program that's going to combine leading edge science and actually making some money, right? I think I was kind of at the right place at the right time. So really in the few years I was there, I was kind of, I felt at times it's the glue between the business strategy and the research and what had been done before. So it was a passion of mine. It was fascinating. And let me just insert one thing about the book. You mentioned Dancing with Qubits. There were a number of books when I started writing that. I started writing in 2018. Number of things on the web, but none of them appealed to me. They all seemed to assume that people had 3 years of graduate physics, which I didn't. And though I'm not embarrassed about it, it's a little awkward when you're trying to talk to experts, right? So I started looking around at what material there was. And I didn't find anything that I really liked that spoke to me in the way I thought. So I thought, if I'm learning this stuff, I might as well write it down. So that's where the first book came from. For people who do not come from a physics background, for people who really start with high school mathematics, and they have to be really interested in the subject, but to bring them through the foundation of quantum computing.
That is amazing. It's actually a perfect book for me. And we are so excited to be sharing quantum with the world, with our investors, with our listeners, with our other Maverick pioneers, because the more we have had these beautiful conversations, the more that we learn that people are coming to quantum through a passion and curiosity. And then they're, as you so rightly said, identifying knowledge gaps. In writing the book, I'm really curious, in your own experience as a student and then teaching others, what are some of the biggest misconceptions or hurdles? One of them definitely was the physics background. I know that's something I've struggled with some of the higher level conversations. Other people thought you needed all sorts of different kinds of math when it seemed to be more linear algebra based, right? Which, with some, college math that I've had definitely is something to, be able to develop. But what were the biggest hurdles that you faced, and then your readers now getting the feedback on your book? What have they thanked you so much for when it comes to making the learning process, when it comes to quantum and quantum computing in particular, easier for them, so they have an entryway into this really exciting field?
I think many people, when they hear about quantum computing perspective, there are a lot of explanations, for example, of the phrase, it's 0 and 1 at the same time. Well, what does 0 and 1 at the same time mean? Is it like 0.5? Is it halfway in between, right?
That's a good question.
And the poor Schrodinger's cat example and things like this. And those are all very physical concepts. And much of our understanding of physics, and this goes back to Isaac Newton, is very based on some real sense, right? We know how the world really is, right? And that's our context, that's our perspective. Well, things can't be two different things at the same time, right? I mean, we all know that. That's ridiculous. Yet somehow quantum does that. And it's like, oh, wow, that's great. That's scary. That's whatever. And it's a concept called superposition. Well, really, to understand this, it's not really a sense of being two things at the same time. It's a question of probabilities, right? That is, you have a sense of the probability of where something is at a certain time. And this very complicated thing, and whether you're talking about energy or any of these things, people use this, the wave function. You got to talk about the wave function. What the heck is a wave function? What the heck is a function? What does a wave have to do with it? So you've already loaded all this terminology onto people. But if you think of the math, all of this reduces to something much simpler, right? So an example, so let's say I ask you to go outside. So you're in Dublin, right? And I say, all right, go 3 blocks north and 2 blocks east, okay? 3 north, 2 east. And I say, isn't it amazing? You are north and east at the same time. And you might say, who cares? That's dumb, right? But it's a similar idea with quantum about 0 and 1. It's not literally the number 0 and 1. There are certain concepts. And so you have a blending of these two things. Just as in directions, you might have a blending. Now, being science, it's a little more complicated than that. And in fact, we do bring in linear algebra. And my little north and east thing is a plane, right? You go first, you go vertically, and then you go horizontally. That's geometry. The extension of that to bigger is linear algebra. If I start asking you, what's the probability of where you'll end up being? Well, again, probability. And then to make it extra fun, we use complex numbers. We don't just use real numbers like pi and 3.8 and negative numbers. We got to throw in that imaginary number as well. And that's what makes everything work. But really, from a foundation of complex numbers, basic probability, and pretty simple linear algebra, the rest of quantum follows. So my thesis, if you will, in writing the book was, if I could lead you along so you have a good, comfortable understanding of these ideas, we can then build on that. And now we can talk quantum. And so the 0 and 1 at the same time isn't a strange concept, but just this very simple expression. And then we can extend that in different ways. So my goal in writing the book was to imagine I was right next to you on a blackboard or a whiteboard. And we're working through that, and maybe you hesitate, and I ask you a question, and we work it out together. By the time we're done, everybody's happy. So that was my perspective on writing the book. And that's the kind of thanks I get from people. To go back to your original question, which was, people would say, I was scared off by a lot of the other books, right? They just seemed to assume too much. You led me through this. I wasn't embarrassed to learn more about this. You could fill the gaps in my understanding so that I could actually get there. And so my goal was to expose a lot more people to quantum computing who otherwise might have been nervous about jumping into this.
And I'm interested in your move from such a large organization of IBM to Inflection. Could you talk a little bit about why did you see this was beneficial, or was it just you had 39 years was long enough?
Yeah. I mean, sometimes I say, look, I was there 39 years. I'm allowed to leave. It's not a lifetime sentence, right? And in fact, that was just full time. I actually started as a summer student 4 years earlier.
Oh my.
Wow.
And yeah, I don't mention that a lot, just because it makes me seem that much older. And I had done a lot of things. And through the years, I had thought I'd really like to do 2 things. I'd like to get back to teaching at some point, and thinking of it a little bit, later or toward the end of my career. And that's the adjunct position at the University of Buffalo. I'm going to be teaching a quantum seminar in the fall. But I also wanted to be at a smaller company. I did big. I think at its peak, IBM had about 400,000 employees while I was there. Any big company does things certain ways, right? That's just natural. They have procedures. I did not really quite one of everything, but I did one of a lot of different things. And so I wanted to join a company that wasn't too big, but was nevertheless mature. So Inflection, and it was called Quanta when I joined, was founded in 2007. Okay, so last year was 15 years. So while being a small company, it wasn't exactly a startup either. It'd been around, but it was expanding and it was growing. And that's what I really like. I like growth. I like getting in there and taking basic ideas and really pushing them out there and getting it going. And then once they get going, I start looking somewhere else. Right?
Get that.
Yeah, that makes sense. So it's basically like the small fish in the big pond and the big fish in the small pond, almost, you know?
That's right. That's right. And I wanted to bring, I mean, a fair number of people knew what I was doing at Quantum and through the books and otherwise. Inflection does what's called a neutral atom approach to quantum computing. IBM does a superconducting approach, and there are many different ways of actually making qubits. Right? So I certainly thought it'd be interesting to learn about something else, another approach. And one thing that you can do with neutral atoms that you can't do with superconducting are things like sensors. So building atomic clocks, actually building radio receivers, very sensitive ones like this, and then sensors. How fast are you going? Are you rotating? Can you measure changes in gravity? So this technology, the neutral atom approach, is very flexible. And so, yes, I'm thinking professionally, but I'm also thinking intellectually, like, wow, more stuff to learn. Yet it's a continuation, it's an expansion of what I was doing. And again, to help a company, get off the ground with us.
Very good.
So you mentioned sensors, and you gave a brilliant talk for The Economist on quantum and the future of quantum. What's so exciting about quantum? And so many people, when you say quantum, are now thinking of quantum computing, but actually, as you enlightened us in the audience, quantum sensing has huge untapped potential. For our audience who is not familiar with quantum sensors and why they would be more precise or more powerful or more desirable, in what ways could or do quantum sensors already revolutionize processes, make things more efficient, or why are they more desirable? And why is this a really exciting terrain for quantum expansion, Dr. Sutor?
Well, one example I give is that people are already using quantum sensors, particularly in the medical field. So we still have X-rays. I just had some dental work done, so I know about X-rays. But if you have very serious conditions, they have to watch how many X-rays they do on you. I mean, X-rays can have a bad effect on you. Moreover, there's only certain things you can tell with an X-ray, right? In terms of the resolution of it, the dimensionality of what you were learning about this. In the 1940s, people started developing technology that was called nuclear magnetic resonance, NMR. And in fact, the person who got a Nobel Prize for this was Felix Bloch of the Bloch sphere fame. It goes back to the 1940s. And that was used starting in the 1970s for MRIs, magnetic resonance imaging. So if you know somebody who's had problems with their knee or their shoulder, or maybe some more serious thing, MRIs were good because they're safer than X-rays and they offer much greater resolution, precision, right? So if you think of an image, right? One with more pixels, one dots, and you can use the quantum effects. In fact, you're basically jiggling hydrogen atoms in your body in water. To get a very high resolution picture of what you're doing, and therefore that leads to better medical diagnosis. So people have been very happily doing the quantum stuff all along. When you go to an ATM, let's say, and I know people are moving to digital cash, but they're still out there. Occasionally I go to an ATM, and you get the receipt at the end. This is how much you took. This is how much you have left, right? And there's a little timestamp on that. That timestamp probably came via a GPS satellite. And in that GPS satellite is an atomic clock, quantum clock. You've been using it all along. Now, unfortunately, those satellites don't have a lot of what's called stability. They don't keep accurate time for very long. So twice a day, the GPS satellites are updated from Earth to just say, oh, here's a more accurate time here. So this notion of stability and accuracy becomes very important. And in fact, the whole issue about GPS is one of increasing concern. If you look at some of the places where people are fighting, battles, war zones around the world, you see what's called GPS denial or GPS spoofing. So imagine that you think you are on a ship in the Taiwan Straits and it tells you you're in the middle of the Indian Ocean. Or imagine you are a pilot in a passenger plane landing in Tel Aviv and the alarms start going off because your system thinks you're in the Jerusalem or in the mountains around Tel Aviv, when in fact you're really just about to land on the runway. So this is spoofing. I read an article several months ago where the amount of spoofing in Israel had reached a 6-month high.
Wow.
Because over in Syria, presumably, the article said there's a Russian military base. Well, there's something else on the Israeli side, right? So one side is spoofing so the other can't do things, and the other side is spoofing so the other person can't do. So you've all got this going all the way out to Cyprus at different times, completely screwed up GPS. Right? Now, GPS, in a somewhat more mundane way, if it's very cloudy, if the weather conditions are terrible, if you're in the mountains, it doesn't necessarily work. So for lots of reasons, people are looking at replacements for GPS. Okay. There's a great book called Longitude that talks about the development of maritime clocks. Think back to the days of wooden ships, and they're setting out somewhere. And what's supposed to be a one-week trip takes them a month because the weather's bad, or they go off course, or all these different things. And the book is called Longitude because while it's relatively easy to determine your position north-south because of reading of the stars, it's not when you're going east-west. There's no natural way of doing this. And so what you do is something called dead reckoning. That is, if you know where you start, if you know how fast you're going, and you know how much time has elapsed, you can estimate somewhat accurately where you are. It's a great old concept. What they used to do is they used to put a log at the end of a rope at the front of the ship, throw it in the water, and then quickly run back, going like 1,001, 1,002, 1,003. That's not the best way of measuring how you're doing. The same thing is happening with quantum sensors. So first, highly accurate, highly stable timekeeping, atomic clocks, because you can't measure changes in distance or space unless you know how fast you're going, which relates to time. Right? Then you have to measure changes in velocity. How fast are you going? Are there changes? When you start, you're going 0, so you can compute, as you increase. So those are called accelerometers. In your smartphone, there's a very inexpensive and somewhat inaccurate one, but it's sufficient for just driving around a bit. So you've got accelerometers, you have gyroscopes. Gyroscopes are absolutely cool. I'll just leave it as homework for your readers to look at something called ring laser gyroscopes. Every plane that you've ever been in, big plane has one of those, every jet. It's a fascinating sort of idea. There's a quantum version that's even more precise in measuring how much you would turn in three dimensions as well. And then there's also gravitational differences, which you might use, for example, changes in altitude, many other applications. So all of these things wrapped up give you positioning, navigation, and timing. So huge application space for commercial. And as you can imagine, the military might care about these things too. So this is a little idea of how sensing, but it all goes to how precise can you measure and the stability of those measurements, because as you move in something at high speed, you're making lots of little changes. You've been on a plane, it's a little bumpy, you're turning a little bit, right? The plane tilts and things like this. Add up all those little changes. You need a lot of decimal places of precision. Quantum comes in to give you all that.
Incredible.
Amazing, amazing. Yeah, it has James Bond movies written all over it, hasn't it?
Yeah, you can imagine, when you might imagine, you can imagine when these things might come in. In 20 years, will you have quantum atomic clocks in your car, right? For better navigation, self-driving, all these things. And 20 years isn't so long, right? I mean, that sounds like it's long now. Yeah.
Sorry, I was just thinking, right, in your journey, since you've joined Inflection, what kind of obstacles, if any, are you coming across?
Mm-hmm. The biggest challenges currently being solved.
Yeah.
So I think, so first let me start with the industry, all right? For a long time, quantum computing had a reputation of always being 10 years away. No matter what year you're in, it's 10 years away.
Yeah.
And I do think it's taking longer than most people expected, right? So to really reach the point where we can put it to practical, let's say commercial use. And in fact, even though we told people it was a multi-year thing, but because it was complicated, you needed to get trained, you need to plan for it. People are getting a little anxious about this. I believe at the conference you mentioned, I used the example of you're going on a family trip in the car, right? And you put the kids in the back of the car and you say, look, this drive is going to take 3 hours. That's how long it takes to get to grandma's or wherever. And after 15 minutes, what do they say? Are we there yet? And you politely say, no, I said it was going to take 3 hours, right? So that is, no, I said quantum computing was going to take 7 years, whatever, right? And then you hear, but I want to be there. And so the industry is saying, but I want quantum computing to be ready today. I'm mad at you for not being ready, and things like this. So part of it is just the natural aspect of, we told everyone it would be multi-year. They're getting a little antsy about this. And the technology's somewhat more complicated, right, to scale up. There are a lot of unknowns about how to do this. I would say the number one issue is, how do we scale these things? How do we really make big enough quantum computers? No one's going to change the world with 30 or 50 or 100 or 400 qubits. Get back to me when you hit 100,000 and maybe even 500,000. And there are going to be some obstacles. You're not going to be able to just have one great big quantum computer with 500,000 qubits. You're going to have to connect smaller ones. We don't know how to do that very well. So there's always a lot of science between here and there. And it's a little bit of an elephant in the room. So scaling quantum computers is definitely going to be an issue, while keeping the performance up, keeping the error rate low, and so forth, and things like that.
And for somebody that has worked with IBM and has seen such changes and such developments in your lifetime, where would you rate the disruption that quantum can or what disruption can it cause? How, because we hear all crazy things that this is going to be like the end of days, like when it comes. So do you think this is going to be sudden, gradual, or is it going to be a major disruptor?
It will be gradual, because initially the quantum computers anyone will use will probably be these supercomputers. There'll be great big things taking up a lot of space in a data center, and they're going to be saved for the hardest problems that either, let's say, a government may want, let's say, an Ministry of Energy or something like this, or defense or something like this, or well-heeled clients such as banks, right?
Mhm.
And things like this. So that will come along. One of the misconceptions I think a lot of people have is that quantum is simply going to replace the computers we have now and be a lot faster at everything. That's actually not true. Quantum is only probably going to offer an advantage in three general areas. And if your hard problem doesn't fall into one of those three areas, you still got a hard problem, right? So either quantum computing won't solve the problem or make it more tractable, right? And that's one of the things that annoys me about some of the hype, saying, well, with the dawn of quantum computing, all hard problems will fall and we'll analyze petabytes of data within seconds. None of those things are true, or will they be true, right? So you have to understand what quantum will be good for, what sort of applications. I think we understand in the data center, the supercomputer approach, people are looking at some applications that might relate to machine learning. Although even there, we have to be careful because quantum computers cannot process a lot of data. So if I'm saying, I'm going to give you an AI problem, but you can't use a lot of data, you're saying, well, but that's what that is, right? Exactly. It's the so-called input problem. We can't get the information into a quantum computer to do anything interesting, but there's some linear algebra problems that we do think it will offer some improvement. Some types of optimization or modeling problems. So we hear about Monte Carlo, right, which is a probabilistic type of technique, goes back to John von Neumann in the 1940s. Things where there aren't exact formulas for getting answers. You do this probabilistic sampling. Financial services uses that a lot because the big range of modeling the world, there's no formula for things like this. And financial services interested because they're financial services. They have a lot of money, they move a lot of money, as we've known from high-speed trading, right? Milliseconds count and things like this. And then the third area is just modeling the universe, modeling physical events. Every single atom, every single electron, every photon of light is quantum. So if we want to say, well, if we want to understand something better or compute a solution, develop some new molecular process, well, I could do it in a wet lab, right? Test tube speakers, all that sort of stuff. Or if I could exactly represent that quantum state in a computer, I could manipulate it there. It's much cleaner, in theory, much faster. So if you're not falling into those three areas, right, you're out of luck. And it is probably the last one I mentioned, modeling physical systems, that we will see the first breakthroughs when they come, or what we call quantum advantage will appear there.
Amazing. Yeah, we did speak to an expert in cybersecurity about the part of quantum when it comes to harvest now, decode later, why people can't say exactly when quantum computers will be powerful enough to crack these encryptions, but the investment in infrastructure does need to happen. Standards do need to be set. Solutions do need to be found, because once that moment has arrived, we don't know what the bad actors are going to do. We don't know how long they have been, waiting things with a whole lot of sensitive and important data actually to decode, right? So we have heard about that. I love in your talk how you talk about that there's so much focus on the hardware, and rightly so, of quantum computing, and when it will actually be viable to solve the different classes of problems that you so beautifully laid out for us. For people who are interested in getting into quantum now, there hasn't been as much focus in the actual software. in the need for software and quantum computing software. And it's a huge passion of mine. And we're doing a really interesting collaboration with a very cool application of quantum computing software now. And I love your teachings on this. So would you share with our audience, why this is important, why people need to be learning about quantum computing programming now and creating softwares and programs that can be even helpful for issues that we have right now before we get even to the hardware maturity?
First, combining your last two questions and topics, it is quantum computing software in the form of algorithms and Shor's algorithm that makes people nervous about the future of encryption. Because if you can factor very large numbers, and indeed factoring numbers, most people haven't thought about since high school, and as an area of interest, why do I care? That goes into it. I would even, though, if I were a security company, I would definitely phrase it as when quantum computers do this. I would actually phrase it a little bit more like if quantum computers can do this. But it's not a safe bet to bet against the possibility. So you shouldn't be skeptical. One shouldn't be skeptical about this, but getting a quantum computer that has 20 million qubits, which is the current, best estimate. The biggest quantum computer has a little bit more than 400. There's a big gap between 400 and 20 million, right?
Got a ways to go, as you said.
Got a ways to go. No one's stealing your credit card via quantum computing on Tuesday, right? And things like this. So software. I'm a software guy. Yeah, when it comes really right down to it. And the industry, the computer industry, is usually dated from about the mid 1940s. And a lot of that early technology came out of really World War II. It was classified technical technology. They were initially calculators, and then they became computers, programmable computers. They were general purpose machines that you could do different things. And then that led to mainframes in the 1960s and things like this, and suddenly exploded, right? Suddenly lots of people needed computers, leading to what seems like millions and millions of apps on iPhones and Androids and things like this. So it's the software that takes advantage of the hardware. And so we need the same for quantum. And also we have to realize that, as I talked about before, quantum's not going to fully replace classical. Anything we do going forward is a combination. We'll use quantum for what it does best, but maybe the whole rest of it is done with classical computers. For example, a very common type of thing in regular classical coding is like, if this condition is true, then do this, otherwise do that. There's no way of expressing that in a quantum computing model. If I were to say, do the following little bit of code 10 times, there's no way of expressing that in a quantum computer. It's just not in the way it works, the computing model. So you need that classical control wrapped around quantum and other classical functionality. So they're going to be mixed in a way. And that's what I was trying to do with the Dancing with Python book, in fact, was because a lot of people use some of the very good API sets, the software development kits like Qiskit and Circ. But we need to have people start thinking about the elements of classical coding, the structures, regular integers, lists of numbers, lists of whatever, and then quantum circuits and things like this and blending them. So I tried with Dancing with Python to have a unified approach to this, particularly for people who are learning coding. We teach quantum to people and teenagers or people in university, right? And things like this. They don't have 50 years, as I do, of classical coding baggage. They don't care that quantum is a different model. All this great probability and things we talked about. Coding is coding is coding, right? So we're using the experience of the last 70 years of understanding software stack, layers of abstraction, and transferring that over to the quantum world and understanding how they integrate. I don't like using the word hybrid. I like to think of them as integrated, right? And that's how we will proceed forward with this integration of the two types of computing.
So as you spoke of, and this is a big passion of ours, which is really transmitting the power of quantum, or quantum adoption, really sparking the curiosity about quantum in people who are kids to teenagers to people who are just starting college, and really showing them that the barrier to entry is a lot lower than they might think. Do you have any advice from your own experience and from your incredible history when it comes to programming and coding for people who would love to get started and learn that's why you created the book, Dancing Python. Is that something that is approachable for someone in middle school? Like what would be good foundations for people to take on board so that their entry into quantum computer programming is even easier?
Middle school may be a little bit early, except for exceptional students who are doing a lot of independent work. Toward the end of what we in the United States would call high school, and I'm not sure what your equivalent is, what form or whatever it is. Let me say when you're about 16 or 17 years old, wherever you happen to be in school, right? Whatever we happen to call it, usually you have picked up enough of the mathematical foundation to get started. So the elements of what we would call here typically in a pre-calculus course, those types of topics. Again, we're talking probability. We're talking a little bit more interesting geometry. Sometimes they cover complex numbers, a little bit here like this, but that general idea is enough to get you going on quantum. One big difference going way back to when I was that age and in school was the material you got was from the teacher and whatever book you were using. So when I was taking calculus in high school, I did actually find another calculus book, but the resources were very limited. You can learn about quantum computing without stepping foot in a classroom or talking to any teacher. Right? There are lots of good courses and things at lots of different levels. And you can use real quantum computers, right? I mean, kudos to IBM. You can use a 7-qubit actual quantum computer across the cloud, right? There are excellent simulators that you can do all of this type of thing on your laptop. So there are far fewer restrictions, and it all comes down to you. How much energy do you have? How much passion do you have? Nobody's standing in your way. Nobody's saying, no, you don't have access. No, you can't get learning material. So if you want to learn, you can find out. And I answer questions. I mean, people find them of all ages on LinkedIn and ask me questions. I think that's really cool.
We definitely know where to come with some of our questions.
Sure. Yeah. Happy to.
And we have a final question to wrap up, and that is quantum legacy. First, personally, how do you see your legacy in quantum? What are things you're still interested in? You told us some of the things you're still really excited about learning about, but in terms of pioneering perhaps solutions too, or if you looked completely back on your time in quantum and what you've produced, your books, what else do you see from the future, looking from the future to right now that you'd really like to do, create, or experience? And then how do you see our world in terms of quantum applications, quantum computing, even our understanding of quantum, maybe 20 years from now?
Well, let me say, clearly my legacy will not be as a quantum scientist or a quantum engineer. I do come, as I mentioned, from this math and computer science background. I am not writing deep research papers. It's been wonderful working with these scientists at first IBM and now Inflection. But kudos to them for building the system and things like this. Personally, I think, I'll tell you, it's education. I mean, if I had to pick one word, it's education. Mm-hmm. On one hand, it's teaching people what it really is. I mean, actually teaching them the quantum computing. For some reason, I've spent a lot of time on LinkedIn the last 2 weeks writing comments. I hope politely correcting certain statements that people have made about the scope of quantum or the actual influence that this new result or that new result will have to cut through the hype to this. So, I'm hoping to be seen as an honest voice that helps people understand and integrate, there's that word again, right? This new knowledge about the value of these quantum technologies with how, what they're doing today and what they're going to do in the future. I would love it, in 20 years when I'm in my 80s, to find out that somebody read my book, Dancing with Qubits, as their first book, and they're like an amazing quantum scientists doing it. That would be so cool. I feel I know people who have gotten jobs in the quantum industry having read my book first, and I think that's really cool too. So that's where I see it's that education in many different ways: business education, the technology education, and just setting up the future, if you will, for this technology, so people can use it wisely and intelligently.
Beautiful.
Very good.
Beautiful. Yeah. And finally, where can people connect with you? Where can they ask you questions? And where is the best place for them to learn more?
So just find me on LinkedIn under Robert Sutor. That's the best way. I often speak at conferences, the usual quantum conferences, and so forth. But I'm very happy to, on LinkedIn, to talk, converse.
Thank you
Excellent.
so much. So to our audience, we couldn't have brought you a more incredible guest when it comes to, just learning more about differentiating the hype from the possibility, as well as really uncovering the amazing opportunities that lie ahead of us in quantum. So thank you so much, and tune in next time for another episode of Quantum Mogul, the podcast. Bye for now.
Bye-bye.